Okay, I am going to continue with the effect of gravitational waves on the matter. Once again, I am Rajesh Nayak from IISCR Kolkata. So, let us start with the some simple important properties of gravitational wave perturbations in flat space time. So, usually the metric with the perturbation is given as a flat metric and gravitational waves which are propagating on the flat space time. So, which we assume the amplitude of these waves are very small, and we have seen that is of the order of 10 to the power minus 23 for most of the astrophysical sources. So, as one sees astrophysical sources, we are very far from the source, and the perturbation can essentially be written as plane waves. That means, the metric perturbation is written as a tensor mu nu and then a plane wave which propagates in some direction which is given by the vector k alpha. So, the amplitude which we have seen, it depends on the total mass of the system, compactness of object or the radius of object, and the plane wave which is essentially characterized by a wave vector. Now, wave vector is orthogonal, no, this should be K A. I am just there is one error I found. So, this need to be K A K A. Okay, let us continue. So, one of the important property of wave vector is k alpha is null. That means, gravitational waves are propagating at the speed of light. So, it is built into theory of relativity that nothing can propagate at the speed of more than speed of light, and consistently incorporating the gravity into special theory of relativity, irrespective of all the complications of theory, the waves, again gravitational waves, propagates at the speed of light. This has been tested to very large accuracy. So, we know that the gravitational waves travel to well known accuracy, that it is moving at the speed of light. Another important property which we call is transverseness of the waves, that is amplitude tensor, that is a mu alpha is always orthogonal to the propagation direction or the wave vector k alpha. So, this is given by this simple condition which says that k alpha is orthogonal to a alpha, and the gravitational waves are transverse. Now, in a suitable gauge or coordinate system, which is called the transverse traceless gauge, the entire gravitational wave perturbation or propagation wave or the amplitude can be written only in terms of two independent quantities, which completely describes the entire waves, and those, that is why we call it a transverse traceless gauge. In that gauge, a constant amplitude which can be written as a x x minus a x x in the diagonal side and a y and AY. So, this completely describes gravitational wave amplitude in terms of two tensors. So, we will come back to that in little more detail while studying the physical effect of gravitational waves. What happens when the gravitational wave passing through a medium or a particle or a system of particle? So, general relativity, the basic underlying physical theory, allows for a point at any given point, allows you to build a local coordinate system in which gravity is completely absent, which is called local flatness. Because of this principle, given single observer or test particle, one cannot predict or predict the passing of gravitational waves. All the effect essentially can be removed because of the local flatness of the space time. So, that means we need minimum 2 particles to determine the effect of gravitational waves. So, let us say that we have 2 point particles which is present, one at the origin whose coordinate is given as zeros because it is at origin, and one lying along x axis at a distance L from the that first particle. Now, we say that a wave is propagating through this. What we do is measure the separation between these two particles. When we say the separation, it is a space time interval which is given by the metric and can be calculated using this equation. In our case, we can put down the exact metric perturbation produced by the gravitational waves at the point x is equal to 0 or the origin, and determine what is the space time separation between these two particles. And with simple calculations, it shows that it is depends on the length and the gravitational wave component h x x in the T T gauge. So, this shows that the effect of a gravitational waves on the particle is essentially the change in their distance as a wave propagates through them. So, this is main principle by which you see whether a wave is passing through a given point or a set of particles. The change in the length is given proportional to the amplitude, and amplitude of gravitational wave changes with the time or this thing, and hence the distance between the two particle would exactly change as the wave propagates through the this thing. So, physical again we say that as a wave propagate through, we keep a set of particle and measure how they are changing. That is what we have seen. The same thing is reformulated or shown as what is known as geodesic deviation. So, geodesics are equivalent of straight lines in the case of curved space time. So, all the free particle which are not affected by external forces are moving along a geodesic. So, that means, when we leave two test particle in the space time, they will be propagating along a geodesic. Now, the connecting vector between the two geodesic is what we see how it changes with the incoming gravitational waves. Now, if the phase time is flat, there is no change, two particle left, they will remain at the same point, that geodesic motion is only they will moving in the time and there is no displacement related to one another. Of course, if the space time is curved, then you have a expression for geodesic acceleration, how these two particles move along is related to Riemann tensor, and if the space time is static or stationary, does not depend on time, then they will be always be not be changing with respect to time. Now, in the flat space time it will remain same because there is no curvature either. So, when the incoming wave comes through and geometry and Riemann curvature everything changes around that, this geodesic would be deviated or accelerated from one another, and that is what gives you is the presence of gravitational waves, and that can be directly related as we have done simply by measuring the distance between the 2 points earlier case. Now, when you have a xi mu as a connecting vector between the two particle geodesics, the geodesic acceleration is directly connected to the space time property, and this is the geodesic acceleration which tells you how two geodesics are changing their distance between them. They are coming closer, going far away, or they are accelerating, decelerating from one another, which is connected to Riemann tensor, the 4 velocity of the geodesic and the connecting vector. So, that is what we call the geodesic deviation equation. Now, when wave is passing through, everything depends on the time. You can explicitly calculate the Riemann tensor given here. It turns out that with the approximation of linearized theory, the Riemann tensor and the everything is essentially becomes a double derivative of the perturbation, that is 2 components. Now, we can take two special cases. We have a wave passing through it. We have a two particle following geodesic, and we see the particle is only on the along the x axis, and that means connecting vector is along x axis. Then the connecting vector xi x and component of y will be changing based on the gravitational wave, and that can be related with this equation. Same way, if the xi is along y axis, that means you have now kept the second particle along the y axis instead of x axis, then both x and y component will be oscillating again, because x and y would be depending on the amplitude of the hxx and hxy component of the metric perturbation. Okay, let us continue with the looking at the effect of passing gravitational waves on two particles, which can be easily generalized to more number of particles. So, what we have is a connecting vector between the two particles, which essentially get accelerated based on the second derivative of the hxx and hxy component of the metric perturbation. So, again last we have seen that the entire amplitude in TT gauge can be written only in two parameters. To be more formal, you can take an amplitude and write them in terms of two linearly independent tensors, which we can say there are two states of polarizations of gravitational waves. Two scalars are amplitude AXX and the AXY. We can say it as amplitudes of polarization, one which we call is a plus polarization and the another one is a cross polarization. Now, once you have a amplitude on the TT gauge, which we have reduced only 4 components, which is now the sum of two independent polarization, which is represented by AXX and AXY. If you have one polarization plus polarization only, then you will have a wave completely written as a AXX into the plus polarization, and if you have cross polarization, then you can write in terms of AXY only. So, since they are linearly independent, you can superpose them all as you want and then find the resulting motion. Now, to study the effect of polarization, it is more suitable to take a ring of particle. So, that means, now instead of taking two particles, you take a ring of particle which are scattered on a radius r. So, you have their position can be given as L cos theta and y as L sin theta, where L is a radius of the ring. Now, deviation is now in terms of two linear independent polarization. You combine all the equations which is there given earlier and see them. For example, we have what happens when the connecting vector is along x axis. It responds to both polarization, that is it responds to x x and it responds to x y. Okay. Let us study the effect of passing gravitational waves on a ring of particle. To study what does plus and cross polarization does to a set of particles. So, we have placed uniformly, let us say x is equal to L cos theta and y is equal to L sin theta. L is a radius of the ring. Now, if we have a particle only in the x direction, two particle, let us say one is in x direction, one is at origin and one is x direction. Now, as both plus and cross polarization pass through it, each of them make it move related to each other. So, both x and y component of connecting vector is changed as per this equation, and the y component is also changed because of x y component of the polarization, x y component. Same way, if you have place the particle along y direction, both polarization plus and cross will make particle to the connecting vector to change both in x and y direction. So, the resulting complete motion would be the change in x and y component based on the plus polarization and change in x and y component because of cross polarization for each of the particles. Now, we are distributing x on the circle. So, x position and y position would smoothly change, and that is represented by theta. When you change theta, both x component y component would change, and each of the components will be affected by both polarization. So, that is summarized by these two long equation. So, you have what happens to x component based on where it is position, x x component of the gravitational waves, and its y component and x y component of wave. That means, plus polarization is going to affect and cross polarization is going to affect through this, and the same way for the y component of the connecting vector would be x component would be connected by cross polarization and y component would be affected by the plus polarization, and whole ring would be explicitly calculated if you put theta with the hxx, and you put all the component for this based on the plane propagating wave. We have full amplitude gravitational wave perturbation, which can be written as a plane wave, amplitude and the time varying part. Everything put together, we can see how entire circle of particle is changing its position when the wave propagates through as a time passes. This is given by these two equation. So, longer equation easier to see through the equation. So, let us say that we have a set of points uniformly distributed over this thing, and plus polarization is going through it. What would happen? As the plus polarization go through it, in the first phase, as the entire cycle of wave passing through, during the first phase the wave will be shrinking along the x axis and expanded along the in presence of both x and y plus and cross polarization. A linear superposition of them would be the resulting motion. Though resulting equation looked very complicated, the easier way is to see that look at one polarization at a time. First, see how the particle behaves when it is a plus polarization, and how does the particle behaves when cross polarization is passing through. Eventually, when both get superposed. So, let us start with the set of particle on a circle uniformly distributed, and let the plus polarization pass through along the z axis and see how the particle behaves. During the first cycle, first half of the cycle, during the period, what you see is the one of the axes get shrunk or smaller. Let us say x axis, all the particles are coming towards 0 along the x axis, and the entire circle becomes an ellipse along the y axis. And when it changes over to the other cycle, the particles again slowly relax and come back to their original shape, and in the second half of the cycle entire thing happens in a reverse fashion, and particle will slowly expanding along x axis and then shrinking along y axis, and then it would reach to a maximum ellipse, and then as the wave changes passes it slowly relaxes and comes back to the original circular shape. So, this process repeats in entire cycle, and the waves as a wave passes, the circle will be becoming expanding in x direction, coming back to original shape, expanding in y direction, become ellipsoid in y direction, coming back to the circle. Entire process is repeated, and that is why it looks like making a plus movement along the x y axis, and that is why it is named plus polarization. Now, same thing we can do with the cross polarization and see what does happen to set of particle on circle. And as a wave propagate during the first cycle, particle will be as if ellipsoid is rotated in 45 degrees, it gets stretched along the diagonal across 45 degrees, reaches to a maximum size, and then shrinks back to the original circle. And in the second half of the period, it shifts its expansion by 45 degree on the other quadrant, and then again becomes an ellipsoid and ellipse and expands, and then slowly shrinks back to the original shape. And that in the first half it goes along x axis, expand, and in the second half it expands along y direction. So, essentially it makes a cross like motion along the x y axis, and that is what we see as a effect of two polarization. When the wave passing through with both polarization, resulting would be sum of these two based on the different components. It would be linear superposition of both these plus and cross polarization, but one can know the these components, one can resolve them and see what how individual components are how what is the strength of individual components. Let us look at the strain produced by the gravitational waves on the system of particle or set of two particle. So, strain is essentially a change in length to original length. So, that is essentially called strain. So, we see that when a wave passing through that, the distance between the point is changed by amount proportional to the polarization h x x amplitude and the length. So, from this we can calculate what is the strain. It is very straightforward to see that the strain induced by gravitational wave is essentially equal to the amplitude of the gravitational waves. So, you can have half, but two polarization combined h x x and h y y plus and cos polarization together to produce equivalent to about h. So, that means that in a astrophysical signal, when it is passing through set of particle, the change in amplitude or the strain is equal to the amplitude of gravitational waves, and from that you can calculate what would be the delta L. Delta L would be essentially L into h. That means, if you take a smaller length object, when the wave passing through it, it produces a tiny change in the length. When you as you increase the length of the object, the change in length because of passing wave is also increases proportional to the length of the object itself. That means, if you keep a 1 meter stick and let the wave pass through it, and it produces an oscillation or the change in length is 10 to the power minus 23. On the other hand, if you keep 10 kilometer long stick, the change in length would be 10 to the power 15. That is because you have 10 to the power 3 coming because of kilometer, and then 10. Okay, it is 10 to the power minus 19 meters. So, this way to have an observable effect change, you increase the length and then you get larger and larger displacement because of the wave. Now, this is essentially what you call is a detector response. Now, in principle, gravitational wave detection is very simple. All you have to do is distribute the set of particles and measure distance between them, and the strain, that is a change in distance to the original distance, is directly proportional to the amplitude of gravitational field. Well, the only problem here is that the strain is of the order of amplitude, and that is of 10 to the power minus 23, and that kind of a distances or displacements cannot be measured easily. To have a approximate sense of what this 10 to the power minus 23 meters is about, you have nuclear length scale, that is 10 to the power minus 18, 10 to the power minus 15 to 80. This means, you are trying to measure about 8th order magnitude smaller than the size of a nucleon. So, this itself is a very challenging from technological perspective. So, that is what makes the gravitational wave detection is makes it almost impossible. So, the fluctuation as the wave passes through is what you want to measure. When you have a ring of particle and wave is passing, they will slowly oscillate, and that is what you are planning to measure, and the strain is small. So, that is why entire detection, though in principle it is straightforward, the practical aspect of this is what is called making impossible possible. It is often ignored earlier as impossible task. Nobody sane would ever try to detect a displacement of 10 to the power minus 23. So, however, all this impossibility is always slowly get possible as someone tries doing it. The first person to try this impossible task was Weber. So, his goal to detect gravitational wave is based on what is known as a bar detector. You have 2 points maybe at the end of the bar. Weber is the first one to try making this impossible possible. His goal to measure distance between two endpoints of an aluminum rod. One can say it is a 2 meter long aluminum cylinder. As wave propagate through, it works like a tuning fork. If the frequency of this tuning fork matches with the incoming wave, it would amplify it, and the ends of bar would be moving, and that would be detected through piezoelectric currents. So, this was implemented, and he had his sensitivity of the order of 10 to the power minus 17. Now, for let us say that you have a black hole coalescence happens some far away galaxy, and the entire wave is passing through the earth. When you see the earth itself is space time, entire space time is affected as a wave passing through, and distances between them change. Now, here is an animation which shows if earth is treated as an object and a wave passing through it, how earth would oscillate when black hole merges, except that this picture has been highly exaggerated. Actual amplitude will be very tiny, of the order of size of an atom. On the other hand, here you can see initially you start with the wave with the very low frequency, that is a chirping wave passing through it. It oscillates slowly, and as the time passes, amplitude increases and the frequency also increases. It oscillates very rapidly, and in the finally it dies down. So, that is a kind of a signal which you are looking for, and Weber could not detect, though he claimed detecting gravitational wave, because his sensitivity was only of the order of 10 to the power minus 17, and while LIGO with the sensitivity of 10 to the power minus 23 could detect a gravitational signal from the merging black hole. Okay, most of the gravitational wave source have to be large masses of the order of solar mass or more, and very fast motion, such as going around each other, merging black holes and so on. One of the stellar explosion which we know visible in the electromagnetic spectrum is a supernova, where a massive star core collapses to form a neutron star or black hole, while the outer region explodes with the full power. Though this is a very energetic event in the electromagnetic band because of the material involved, plasma and protons, neutron and other particle accelerated very high speed and so on. These not necessarily be very strong event in the gravitational waves. One reason is it is the asymmetry which is producing the gravitational wave, not the explosion itself. However, supernova explosion is a very complex process, and modeling has been not so easy. In a very recent years only, it is possible to model supernova explosion and see what kind of a gravitational wave radiation is coming. And it turns out that the masses movements are relatively smaller, of the order of 10 to 20% of solar mass, and that makes it they are not very powerful sources in the gravitational wave signal. However, if one finds such sources in the nearby galaxies or in our own galaxy, there are probability of supernova every a 30 years or so, and one can study what happens in the process of supernova explosion. So, in that respect, this is one of the very interesting topic. So, people have simulated, Fuller et al. 2015 have shown that the amplitude, how or what is the signal of core collapse supernova. In this case, the carbon or oxygen core collapses to form a neutron star or black hole. So, in the initial phases, as the eruption happens, at some stage the core bounces and explodes, that probably shock waves comes out from it, and that is what is shown in this plot, where you have the explosion, and the gravitational wave signal is essentially shown here, and one need to be sources to be relatively closer to see. On the other hand, you can also see several in the, when you do it on the Fourier domain, the signal coming out from a supernova explosion, you see the various modes of the oscillation or this thing of the stars as well as a system, which will help you to understand what is the process involved in a supernova explosion. So, one hopes that close by supernova may be observable. The stochastic gravitational wave background from cosmological sources have been one of the interests, and Bicep some time back claimed to have detected signal from the early phase of the universe, somehow which need to be confirmed independently, and this stochastic wave is essentially because of the various high energy events happening in the early phase of the universe, and which passing through the entire universe and come to the present era and such. We can not only study what happened in the beginning, and also as the wave propagates, it carries the information through of the media what it encounters. With respect to early universe, electromagnetic spectrum is essentially coming from CMB, where the matter decoupled from the radiation, and you do not see behind the CMB curtain. On the other hand, gravitational waves would have been emitted much earlier, and if you detect signal from the early universe, then you can probe the universe much more closer to the Big Bang than the cosmic microwave background, and would help to understand what are the phenomena happening in the early universe. So, in all, gravitational wave offers a new window into universe. The information carried by the gravitational waves are completely orthogonal to current techniques such as we have electromagnetic radiation, which has an entire spectrum from gamma rays to radio waves. You can it is each band is important because the mechanism by which energy is emitted is different in each band, while gravitational waves are emitted completely different physics because of a large case motion and so on. So, it gives you completely different information about the large scale motion of the system, and one can model. We have seen, based on the neutron star merger from LIGO detection to gamma ray from Fermi to optical and radio telescope, entire band has enabled us to understand somewhat better what happens during a neutron star merger and its interaction of the matter with the surrounding interstellar matter. So, we expect with gravitational wave detector around the world, we will see more of have a better understanding of the universe. Human race was always interested to understand beyond day to day life and try to understand what is universe and creation is all about. Every given phase, a best of human mind have tried to understand universe and build the model of the universe, and that model kept on evolving, and at each phase they thought they have almost completely understood the universe, and there is a little more work left in future to understand. So, this is a model of a universe based on about thousands of years back, 2-3,000 years back, where you have constructed a model based on understanding there, and our understanding of the universe comes from the data and methodology available current, which we believe to be as correct as people in the past believe how good their model is. As we take more and more data, we probably would improve and understand universe better, and gravitational wave probably would help us to give orthogonal information in and try to contribute to our knowledge about the universe.